NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams. And all these little dots are stars?
All these little dots are galaxies, some of which are bigger than our own.
Breaking news. We may have just found potential evidence of intelligent life beyond Earth.
This is a huge discovery, and we think that it's a huge discovery. And that's the most exciting piece of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect, that we can't explain, because that means that we have to revise our understanding of the universe.
Pluto is a distant and mysterious, more modest planet that was once a singular individual from our planetary group. However, late disturbing statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have carried Pluto back into the spotlight with dazzling exposure. They suggested that this chilly world is on a potential collision course with Neptune. Yet how could this end up working, and what may be the results of such a colossal event? Are we seeing a captivating cosmic characteristic, or is there something else to this approaching boundless accident? Join us as we examine the possible results of a Pluto-Neptune impact. Pluto, a previous planet that was downsized to a dwarf planet, remains a subject of interest and focus in the cosmic community. As per ongoing forecasts by leading specialists, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous collision between these two planets, which could pose an enormous risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a shocking 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. Yet the intrigue doesn't stop there. Pluto's orbit is marked by its extremely elliptical shape, wandering significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets whose orbits lie mostly near the ecliptic plane, Pluto's orbit stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms asynchronous libration and degree libration, along with the VSK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is asynchronous libration. As for Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Extension libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential impacts. Another critical factor in this scenario is the VSK oscillation, named after three scientists, Zell, Kai, and another researcher, who studied how objects move in space. It involves the way three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. this pulling affects how they move. In Pluto's case, the VSK oscillation helps us understand why its orbit close to the Sun is so unusual. Despite Pluto's orbit seeming erratic, this oscillation helps keep it moving smoothly over long periods. The VSK oscillation shows that although things in space may appear chaotic and irregular, some patterns and rules maintain order. These factors help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or drift off course. This three-body problem is crucial in understanding how these orbits evolve, based on how space objects pull on each other. Studying this helps us learn more about Pluto and our solar system, as well as distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is indeed volatile, with small deviations in initial conditions leading to enormous differences over millennia. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively preventing any conflicts. Recent virtual simulations have helped us understand how the large planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune is not alone in this process. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit. Moreover, Saturn contributes as well. These studies show that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a steady path for a long time, perhaps even millions of years. So, maybe Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are essential for maintaining order and stability in space. Without these components, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could crash into others or be ejected from their stable paths, triggering a chain reaction with other celestial bodies. For Pluto, in particular, with discussions about it potentially crashing into Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. Pluto's case shows how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies. Exploring the depths of space often leads us to confront the strange nature of celestial bodies and their complex behaviors. Pluto's unique orbit and the potential interaction with Neptune serve as a reminder of the unpredictable forces at play within our solar system. While many might see Pluto as a distant, almost forgotten dwarf planet, its journey through space challenges our understanding of orbital dynamics and the stability of planetary systems. The study of Pluto and Neptune's gravitational interactions allows us to grasp the intricate balance that keeps these distant worlds in their respective orbits, while also revealing how such an event could unfold in the far future. The possibility of a collision, though highly unlikely due to the stability mechanisms in place, raises intriguing questions about the nature of celestial mechanics. As we continue to explore and learn more about Pluto, Neptune, and the broader solar system, it becomes clear that our understanding of space is far from complete. Every new discovery sheds light on the mysteries of the universe, reminding us that even the most seemingly stable parts of the cosmos are subject to forces that we may not yet fully comprehend. As technology and observational techniques continue to advance, scientists are gaining new insights into the behavior of distant planets and the potential risks they pose. The possibility of a future event like a Pluto-Neptune impact remains a subject of great interest for astrophysicists. Yet, it is also a testament to the complexity of space that such an event, while fascinating, is highly unlikely due to the natural mechanisms that protect our solar system from such dramatic occurrences. In conclusion, Pluto's orbit and its interaction with Neptune serve as an extraordinary example of the intricacies of celestial mechanics. These fascinating phenomena remind us of the importance of continued research, observation, and exploration of the universe. Each discovery not only answers existing questions but also opens new avenues of inquiry, ensuring that our understanding of the cosmos continues to evolve, deepening our connection to the vastness of space. The study of these distant worlds offers us a glimpse into the incredible forces that shape the universe, encouraging us to look beyond our immediate surroundings and consider the broader forces at work in the cosmos. Bodies and Pluto's circle are a perfect representation of the unusualness of orbital disorder. This idea alludes to the sensitive dependence of a celestial body's orbit on its initial conditions, which is clearly illustrated in Pluto's case. Even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using computational simulations has been immensely helpful for scientists in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other celestial objects, like Neptune, interact gravitationally. By tweaking small details in these simulations, astronomers can see how minor changes can have a major impact on where Pluto ends up. In the late 1980s, simulations revealed something intriguing about Pluto's orbit. Despite having mechanisms like axial libration and mean motion resonance to maintain stability, its orbit can still be unpredictable. A small difference in Pluto's starting position or velocity can result in an entirely different orbit after several years. Yet, even with this chaos, Pluto's orbit remains stable over extremely long periods, such as billions of years. This means that Pluto's journey around the Sun has a kind of order, even though it initially appears chaotic. Predicting celestial events, particularly when they involve turbulent orbits like Pluto's, is a significant challenge. The inherent unpredictability of such systems means long-term forecasts are often fraught with uncertainties. While mathematical models provide powerful tools to understand and predict the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Additionally, the chaotic nature of planetary orbits like Pluto's reminds us of the ever-changing and dynamic nature of the universe. While we have made great strides in understanding space, Pluto's case serves as a reminder of how much our knowledge of the universe remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can profoundly influence the stability and trajectory of other bodies within the system. So why are prominent astrophysicists now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist and a prominent figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's fascination with the uncharted realms of space. His stance on Pluto's reclassification reflects the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a testament to how much there is still to discover in space. The allure of these unknowns keeps the study of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that many more mysteries await discovery. Will Pluto collide with Neptune? Or is this another moment of confusion in the ever-shifting universe? Only time and further research will tell. For now, we are left with a deeper appreciation of how much we still do not know about our own solar system. We continue to study these celestial phenomena in the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises new questions about the unpredictable and captivating universe we inhabit. It challenges conventional interpretations of planetary stability. The idea that two celestial bodies with such drastically different characteristics could collide is both unsettling and fascinating, especially given the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is a gas giant with a strong gravitational field. The implications of such a collision would be significant for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential collision, one must first consider the composition and characteristics of both planets. Pluto, despite being a dwarf planet, contains various elements and compounds thought to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere primarily composed of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a gas giant, is mainly composed of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would dramatically impact their structure and behavior, potentially creating a spectacle visible across vast distances. What makes this hypothetical collision particularly intriguing is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. Jupiter, the largest planet in the solar system, exerts a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune less likely. Recent research has also shown that the interaction between Pluto and Neptune is not as straightforward as a direct collision course. The gravitational resonance between the two planets, where Pluto completes 2 orbits around the Sun for every 3 of Neptune's, creates a sort of celestial lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. The orbital mechanics of these bodies are finely tuned to minimize the potential for conflict. Nevertheless, despite this stability, the long-term future of Pluto's orbit remains uncertain. As the solar system continues to evolve, subtle changes in the positions and gravitational influences of other bodies could disrupt this delicate balance. For example, if Neptune's position were to shift over millions or billions of years, it could potentially push Pluto's orbit into a more chaotic state. This type of instability could lead to a collision, or it could eject Pluto from the solar system altogether. Astronomers are also exploring the possibility that the outer reaches of the solar system may contain other, yet unseen objects that could influence the trajectories of bodies like Pluto. The discovery of distant objects like Eris and Haumea has already expanded our understanding of the Kuiper Belt, the region of the solar system beyond Neptune that is home to Pluto and similar bodies. These objects may exert gravitational forces that subtly alter Pluto's orbit, further complicating predictions about its long-term stability. In addition to external gravitational influences, the Sun itself plays a crucial role in shaping the orbits of the planets and other bodies in the solar system. The Sun's gravity is the primary force that governs the overall motion of the planets. Over time, changes in the Sun's energy output, such as the expansion of its outer layers as it approaches the end of its life cycle, could significantly impact the orbits of distant bodies like Pluto. These changes could potentially push Pluto closer to Neptune, increasing the risk of a collision. The ongoing study of Pluto and Neptune's orbits will continue to provide new insights into the complex mechanics of our solar system. As technology advances, astronomers can monitor the positions and movements of these distant bodies with greater precision, offering a clearer picture of their future paths. Despite the complexity of the forces at play, the likelihood of a collision between Pluto and Neptune remains low in the near future. However, it serves as a reminder of the unpredictable nature of the universe and the mysteries that have yet to be uncovered. Ultimately, the idea of a Pluto-Neptune collision may be more of a speculative curiosity than an imminent threat. Still, it highlights the importance of continued observation and the need for a deeper understanding of the forces that shape our solar system. As we continue to study the interactions between celestial bodies, we gain not only a better understanding of the mechanics that govern our solar system but also a greater appreciation for the delicate and dynamic nature of the universe itself.